Okay, let's finish up 4.2 and then move on to the beginning of 4.4. The only objective we haven't covered in 4.2 is Objective 5, recognize and use the Pythagorean identities. These are three properties of trigonometric functions that we're going to use a lot all semester. The first one I'm going to call the granddaddy of all Pythagorean identities, and you can derive it either from the right triangle definition of trig functions or the equivalent definition of trig functions in terms of the unit circle. The very first thing that you learned about right triangles is that leg square plus leg square equals hypotenuse squared. The way I have my right triangle labeled, that would be a squared plus b squared equals c squared. Now, if you divided each side by c squared, you'd have a squared over c squared plus b squared over c squared equals c squared over c squared. And then remember, those ratios of sides of a triangle are are the trigonometric functions. So with respect to this angle t, which trig function could we put in the place of this a squared over c squared? A is the opposite side, c is the hypotenuse, and it's sine that uses the opposite and the hypotenuse. So that a squared over c squared is sine squared of that angle t. And then with respect to the angle t, b is the adjacent side and c is the hypotenuse. So this ratio of b squared to c squared, that's cosine squared of the angle t. And then on the right-hand side, c squared divided by c squared, anything divided by itself is 1. And that's our granddaddy of all Pythagorean identities. Sine squared plus cosine squared equals 1. Now, like I said, you can also get that Pythagorean identity from the definition of the trigonometric functions of some angle t on the unit circle. If this is a unit circle, then sine of t is just your y-coordinate, cosine of t is just your x-coordinate. The equation of the unit circle we've talked about before is x squared plus y squared equals 1. And if x is the cosine of t, again, t has to be an angle in the unit circle, but if it is, then the x squared is just cosine squared of t. The y squared is just sine squared of t, and then cosine squared plus sine squared is 1. So we get the same granddaddy of all Pythagorean identities, whether we use the definitions from the right angle definition of the trig functions or the unit circle definition of the trig functions. That's our big first one. I'm going to put in this blue box, sine squared t plus cosine squared t equals 1. And there are two other big Pythagorean identities. They can be obtained by taking that first trig identity, sine squared plus cosine, oops, I almost left out my angle. Sine squared t plus cosine squared t equals 1. And then just see what happens if you divide both sides by sine squared. Well, that first ratio, sine squared over sine squared, that's just 1. The second fraction, cosine square over sine square, well, that's cotangent squared of the angle t. And then the right-hand side, 1 over sine squared, that's cosecant squared of t. And that's our second Pythagorean identity. 1 plus cotangent squared t equals cosecant squared t. Now you may have to pause the video to write down what I've written down. That's fine. Just pause and then pick back up when you have gotten everything written down. Our third Pythagorean identity comes from taking our first one, sine squared t plus cosine squared t equals 1, and dividing all three sides by cosine squared t. If you reduce each of those ratios, sine squared t over cosine squared t, that's tangent squared t. Cosine squared t over cosine squared t is 1. And 1 over cosine squared t is secant squared t. And that's our third Pythagorean identity. I'm just going to draw a little arrow since I don't really have room to write it in that box anyway. So those are our three big Pythagorean identities. We are going to use them for several things. Probably the most important one in Chapter 5, we're going to do some trigonometric proofs. And we'll have to figure out, one of our tools is using Pythagorean identities in our proofs, and we will have to determine which Pythagorean identity will help us prove what we're trying to prove. But that's not what we're doing right now. Right now we're just using one of the Pythagorean identities to find the values of the others. Now this checkpoint says sine of t is a half. T is between 0 and pi over 2. Well, that means t is in quadrant 1, because pi over 2 is 90 degrees. From 0 to 90 degrees is quadrant 1, and sine of t is a half. So it says find the value of cosine using a trigonometric identity. If you give me a value for sine and you ask me for a value for cosine, I need the trigonometric identity that has sine and cosine in it. And that's the granddaddy of all Pythagorean identities. Sine square, I started to say x, but our angle here is t. Sine squared t plus cosine squared t equals 1. I just thought of something that I'm not sure I've told you yet. Just in case I haven't, I'm gonna put a note over here to the side. Whenever you have any trig function being squared, that could be sine squared or cosine squared, any of them. Make sure you understand that it's the trig function or the trig value being squared, not the angle, not x. So whenever you see trig squared of x, you can write it as the trigonometric value of x, whichever trig function we're talking about, and then square that whole thing. That's what trig squared of x means. So back to this checkpoint that we're doing, if we know sine of t is a half, then sine square of t is the sine of t squared. And cosine of t, I'm going to write that as cosine of t squared, just to keep it really straight in my head, and that right-hand side equals 1. I'm just solving for cosine t. So 1/2 squared is a fourth. If I subtract a fourth from both sides, I have cosine squared t equals 3/4. And then I need to take the square root of both sides. And I have cosine t equals, well, whenever I take square root of both sides, I have to remember the positive or negative square root. And I can simplify square root of 3/4 to square root of 3 over square root of 4. I'm just going to call it square root of 3 over 2. Now we were looking for the value of cosine t, given that t was a first quadrant angle. Here we have two answers. We have cosine t is positive square root of 3 over 2, and cosine t is negative square root of 3 over 2. Which one of those is in quadrant 1? Well, the positive square root of 3 over 2 is in quadrant 1. The negative, I'm just going to say it's not in quadrant 1. So that's not the angle we're looking for. Now this particular problem, we didn't actually have to use a Pythagorean identity. If you just think about the first quadrant angle whose sine is a half, sine's your y value, and your y is a half at pi over 6. So what's the cosine of pi over 6? It's that square root of 3 over 2. But if I gave you sine of t as some value that you don't have memorized on the unit circle, then you could have solved for cosine of t just using this Pythagorean identity. All right, that's all that's left of 4.2. Let's move on to 4.4 because we did 4.3 before 4.2. The first objective in 4.4 is use the definition of trigonometric functions of any angle. In 4.2, we found trigonometric functions of angles on the unit circle, but this section tells us we don't have to be using the unit circle. We can be using any circle of any radius. The radius, let me back up and say this first. This first illustration, these 4 graphs, show me an angle theta in quadrant 1, and then an angle theta in quadrant 2, and an angle in quadrant 3, and an angle in quadrant 4. Let me see if I can get to my highlighter right here. Using some point on the terminal side of any angle theta, you can form a right triangle by either raising or dropping a vertical line to the nearest x-axis. If you give me a terminal side of an angle containing some point xy, then I can drop a line down to the nearest x-axis, and I've made a I'm going to erase that because it's getting too... I can drop a vertical line down to the nearest x-axis, and I have formed a right angle, an angle theta. The horizontal distance from the origin to that vertical line is x. The vertical distance from the origin to that vertical line is y. And if I have two sides of the right triangle, then I can find the hypotenuse. The hypotenuse is the square root of leg squared plus leg squared. And then I can find all 6 trigonometric functions of theta. My sine of theta would be y over that radius. My cosine of theta would be x over that radius. And my tangent of theta would be y over x. And it doesn't matter in what quadrant you draw an angle. The C part of that illustration shows me a 3rd quadrant angle with its terminal side right here, and it contains some point xy. So I can raise a vertical line up to the nearest x-axis, and I have formed this little triangle theta right there. The short side of that triangle, the horizontal distance is x, the vertical distance is y, and my radius is again square root of x squared plus y squared. So the sine of that angle theta would be y over this r, the cosine of theta would be x over r, and the tangent of theta would be y over x. All right, let me sum this up with what is stated in the blue box. Let theta be any angle in standard position. Let point xy be a point on the terminal side of theta. Then you can either drop or raise a vertical line to the nearest x-axis, and it will be the hypotenuse of a right triangle. That hypotenuse will be the radius of the circle. So you can always find it by taking the square root of leg squared plus leg squared. Now, the 6 trigonometric functions of theta are defined by the following ratios. Cosine of theta is the x divided by r. Now, if we were on the unit circle, the radius would be 1, so cosine theta is x. What we're learning now is that what we learned yesterday, the cosine of theta is x, is just a specific case of what we have in the blue box now. The specific case is if the radius is 1, cosine theta is just x. But if the radius is anything else, then cosine theta is x divided by r. And sine of theta would be the y divided by r. Again, if you're on the unit circle, your radius is 1, then sine of theta is just y. But for any other radius, sine of theta is y divided by that radius. All of the other 6 trig functions can be obtained from those 2. Tangent theta would be the y divided by the x. Secant theta would be the r divided by the x. Cosecant theta is the reciprocal of sine. It's r divided by y. And cotangent theta is x divided by y. So let's do this first example. For the point 1, -3 to be on the terminal side of theta, find each of the 6 trigonometric functions. Now, let me see if I have, I'm going to try to draw this in the margin on the left. The point 1, -3 is in the 4th quadrant. Right here. I'm going to scoot that one over, give myself a little bit, actually let me, try to give myself just a little bit more room. Here's, let's say that's 1, and here's the point 1, -3. That's a point on the terminal side of theta. If I raise a vertical line up to the x-axis, then I have formed a right triangle with this angle being my theta. And if this is the point 1, -3, then this horizontal distance is 1, And this vertical distance is, well, it doesn't really make sense to say a distance is negative. I can say, I'm going to write that negative so I don't forget it. 3 below the x-axis, y is negative 3. And then by the Pythagorean theorem, that radius, this r, would be the square root of leg squared plus leg squared, or square root of 10. If that radius was 1, then the sine of that angle theta would just be the y value negative 3. But because the radius is not 1, sine of theta is that y value divided by the radius. In my lab, you'll probably have to rationalize that. On the test, the directions say, don't worry about rationalizing, trying to save you a minute. Cosine of theta would be adjacent divided by hypotenuse. That's 1 divided by square root of 10. And again, in the homework, you'd have to rationalize it. Tangent theta is the y divided by the x, the negative 3 divided by 1, or just negative 3. Cosecant theta is the reciprocal of sine theta. We don't usually leave that negative in the denominator. Secant theta is the reciprocal of cosine theta. And cotangent theta is the reciprocal of tangent theta. So the moral of objective 1 is, if you're not on the unit circle, if your radius is not 1, then your trigonometric functions have to take into account the radius, in that sine of theta is not just 1, sine of theta is not just y, it's y divided by the radius. Cosine theta is not just x, it's x divided by the radius. All right, one other objective. And I'm going to explain this a little bit differently than is in the book. The book gives you an acronym that you can use to remember which trig functions are positive in which quadrants. That's something I don't need an acronym for. I already know the sign of the x and the y in each quadrant. In quadrant 1, your x and y are both positive. In quadrant 2, your x's are negative and your y's are positive. In quadrant 3, both coordinates are negative. And in quadrant 4, your x's are positive but your y's are negative. You can use that information if I tell you the sign of 2 trig functions and ask you, in what quadrant does this angle lie? For example, if I say sine of theta is less than 0, that sine of theta is negative. Well, sine is my y coordinate, and my y coordinates are negative in quadrant 3 and quadrant 4. So I'm going to say this could be 3 or 4. And then cosine theta is supposed to be positive. This is my y, this is my x. My x's are positive in quadrant 1 and quadrant 4. So if you ask me in what quadrant are both of those things true, I'm going to say, well, for both of those things to be true, theta would have to lie in quadrant 4. Quadrant 4 is the only quadrant where sine is negative and cosine is positive. Or you can think of it as y is negative and x is positive. The second one says if secant is greater than 0, well, secant's the reciprocal of cosine, and cosine is your x. Taking the reciprocal doesn't change the sign of that function. If 1 over x is positive, then x has to be positive. And x is positive, we already said in the example above, x is positive in quadrant 1 or quadrant 4. And then for tangent to be negative, your y divided by x would have to be negative. In which quadrants would your y divided by x be negative? Well, in quadrant 2, you're dividing a positive by negative. That would give you a negative. Quadrant 4, you're dividing a negative by a positive. That would give you a negative. So the two quadrants where tangent would be negative would be quadrant 2 or quadrant 4. So the one quadrant where both of those things would be true, the one they have in common, is quadrant 4. Your x's are positive, so your secants are positive. Your y's are negative, so your y divided by your x is negative in quadrant 4. All right. One more example. Kind of a short day. Given that tangent theta is negative 1/3 and cosine theta is less than 0, find sine theta and secant theta. Now, if you need another example like this, there's one just like it, example 4 on page 572. But I think the first thing we need to do is figure out in what quadrant theta lies so that we can draw this. It helps me to picture it if I sketch me a triangle. So I'm going to do that. But first I need to figure out in what quadrant I should sketch a triangle. Well, like we said, tangent is negative in quadrant 2 and in quadrant 4. And cosine is negative wherever your x's are negative. Your x's are negative in quadrant 2 and quadrant 4. So the one quadrant where both of those things is true is quadrant 4. Now, I don't have to draw a picture to figure this out, but it helps me. It really helps me picture what's going on. So I'm going to draw me a fourth quadrant angle . Here's a fourth quadrant angle. If I raise a line up to the nearest x-axis, then I have formed a right triangle with my angle theta being that little acute angle. And if tangent is negative 1/3, then 1 is your opposite side and 3 is your adjacent side. Which one's negative? Well, in the fourth quadrant, it's your y that's negative. So your y is negative 3. Your x is 1. And then just double check it. Have I drawn my picture correctly such that theta, such that the opposite over the adjacent for you know what? I did not draw it correctly, so I'm glad that I was checking this. Wait. Tangent is opposite. Oh, I have it right here, but I put it wrong on my picture. Glad I can erase there. Erased more than I wanted to. But I think I can redraw it quickly. All right, opposite is 1, and adjacent is 3. Only in the fourth quadrant, we know that 1 has to be negative. Now, is tangent theta negative 1/3? Yep, opposite over adjacent would be negative 1/3. So I could find the hypotenuse of that right triangle. Actually, it's the same right triangle that we had in a previous example. Our point 1, -3 is the point that would be on this terminal side of that angle. The radius here would be square root of 3 squared plus -1 squared, or just square root of 10 again. Now that I have that drawn, I can answer the two questions. I'm asked to find the sine of theta. The sine of theta would be opposite over hypotenuse. And in the homework, rationalize it, but not on the test. And then secant theta is the reciprocal of cosine theta. Cosine theta would be adjacent over hypotenuse. So secant theta is hypotenuse over adjacent. And I could find the other 5 trigonometric functions if you ask me to. All right. That's all we need to cover for today. The homework assignment 31 includes the Pythagorean identities from day 2 of section 4.2 and the first 2 objectives in section 4.4. If you have any questions, just email me.